Part 1 to 3 is already available. What I'm going to do now is this part 4. Hey, we did the steady state of this. The steady state, this capacitor opens up, and then, we found the voltage across the capacitor. Did we solve this problem in this class? I suppose yes, RC circuit. We did. Okay, I have done that. In the recorded videos, what are the typical modifications and questions? What else can they ask? I have addressed that issue. Yeah, okay. Did we do this inductor problem? So what the question asks? So they are changing this SPDT switch. Essentially, there is this position 1 and there is a circuit with the voltage source. Position 2, there is a circuit without the voltage source, right? Once the circuit is in position 1, the circuit is in steady state. Then they change the switch. The energy dissipated in position 2 is. Did we do this problem? So position 1 circuit is essentially you have a voltage source with one resistance. What happens in even position 1 is concerning steady state, right? So this inductor is essentially shorted. Okay, the inductor is shorted, and then there is just a voltage resistor circuit. You can find the current in it. The steady state current of position 1, right? That is the initial current in the inductor can be obtained. That happens to be 2. This is a simple circuit, right? Voltage is 15, this resistance is 25, current will be 50 by 25, that is 2. What they are asking is, now we change the switch to position 2. It's a LR circuit. There are two resistances, 25, 25 and an inductor, right? And then what is the energy dissipated in the resistors? Total energy dissipated in the resistors. You could do this by two means, okay? Find current as a function of time. The initial current in the inductor, then it will be exponentially decay. You can find that current as a function of time. And then find, based on the current, the power, right? You can integrate the power to find the energy. This is going to be slightly harder, but there is a very simple way to do it, okay? The idea is, the total energy dissipated in the resistors should be equal to the initial energy stored in the inductor. The analogy I gave, which many students like this, the initial energy stored in the inductor, right, due to a current of 2 amps, that corresponds to the, your full tiffin box that you take to college for lunch, right? That full tiffin box eventually get distributed to your friends and yourself, right? Couple of resistors, right? So the initial content of the tiffin box eventually get distributed to you and your friends. You and your friends are like resistors. The initial content of the tiffin box is like this inductor. So total amount of food consumed by you and your friends together from this tiffin box is the initial content of the tiffin box. So instead of finding, how much you eat as a function of time, hey, what is the initial content, total amount of food available, or the total initial energy available? If you know the current in an inductor, you can find that, right? IS2, energy of that inductor is half Li square, right? Even L is given, and half Li square, you can easily find the initial energy in that inductor to be 0.2 joules. Eventually, all of that energy get dissipated in the resistors. So energy dissipated in the resistors is also 0.2 joules. Fine. So the second method is fairly easy. Total energy dissipated equals initial energy stored in the tiffin box is essentially a statement on mass conservation. This is a statement on energy conservation. Okay. And of course, I have discussed few other things in the recorded video. You could take a look at it. So the bare minimal things you need to know here is, V is IR. Okay, this power is I square R. For a capacitor, I is C dV by dt. We discussed this. Energy is half CV square. Voltage is LdA by dt, and then energy is half La square. If you look at first order transients, exponential decay, if you know the time constant, you pretty much know everything about the curve. We have a very separate video on this, right? The most important topic for gate exam or gate biomedical exam. So you know the time constant, that is RC. Here the time constant is L over R. So if you know the initial current, you know how it decays as a function of time. You can find the current at any point in time. Again, if you know the current in any point in time, actually you can calculate the energy in the inductor at any other point in time, right? The initial energy is one thing, half Li square. You could also do that calculation for any other time. So all this discussion I have already, put up in the recorded video. Do you have questions on this solution? 0.2 joules. So this is 1 by 2 into 0.1 into 2 square. Okay, inductance is 0.1 Henry. Okay, now we are going to look at, so this is a time response, time dependent response, right? Things are functions of time. Now in today's class, we are going to look at frequency response. Things are functions of frequency. Again, I ask you to come prepared with the recorded video, but I'll give you a quick overview. Okay, here if you know this much, it suffices, right? That's what I said. Here, if you know this much, this is the most important thing that you need to know. Okay, for a capacitor and inductor, know the ratio of voltage and current. These are functions of frequency. That ratio is known as resistance in case of a resistor. V by I is R, right? Here, V by I, we call that as impedance. Impedance of a capacitor is 1 by j omega c. Impedance of an inductor, right? That is ratio of voltage to current is j omega L, where j is this complex number square root of -1. This is that one thing you really need to know to proceed further. And if I remember, okay, I have given you the list of parameters involved here and all the parameters and the definitions, SI units and all that. Okay, you can go over this. Yeah, what I am actually go do today is, if you know how to solve resistance circuits with resistors, if you know complex arithmetic, if you can add and subtract complex numbers, if you can multiply and divide complex numbers, you can do all of those analysis even for AC circuits. Point number 1. Okay, I'll try to show examples through PYQs. All the SI units are discussed here, listed here. Okay, stick to SI units, you will actually avoid a lot of headaches. The bare minimal parameters that you should be very clear on: angular frequency, time period, time constant. Okay, given one, you should be easily able to find the other. All the relations are again given here. Okay, time period by definition is inverse of frequency. 1 by time period is frequency. Okay, and angular frequency is, you know, the time it takes to traverse 2 pi radians. That is 1 full cycle that happens in 1 time period. So if you, this is angular speed essentially. If you take the angular distance divided by the time taken, you get the angular speed. So 2 pi by t is a relation, you know, it essentially gives you angular frequency. And I just mentioned by definition 1 over t is frequency. So you also have it as 2 pi f. That is mentioned over here. And quickly you will realize last 15 minutes, 30 minutes, you have solved most of the questions that you know. Okay, I have listed 3 things here as magic frequencies. This is when you don't know, they are asking you for some frequency and you don't know the answer, or you don't know how to solve that exam. Okay, you don't know how to solve that, some scenario like that. Last 15-30 minutes. And you have time and you are trying to get a couple of more marks. Okay, one reasonable guess in that worst case scenario is like, if it's an RC circuit, calculate this as the frequency. Of course, this is in hertz. If it's an LR circuit, calculate this as the frequency. If it's an RLC circuit, calculate this as the frequency. I'll show you examples today based on PYQs. Okay. Notice what we have here is essentially 1 by 2 pi time constant RC. This is also 1 by 2 pi time constant L over R. This happens to be 1 by 2 pi square root of L. Okay. And because we know that 2 pi f is essentially omega, we can also see that omega happens to be 1 over tau. We also can see one more relation over here. Again, I have written that relation in this question. So in fact, I'll start with this question, okay, today. I'll show you examples of very, very simple use of Phasor convention and your applications of Phasor. Some PYQs using magic frequency that I mentioned. And then I am going to treat most of the PYQs, right, as a resistance circuit because I know how to calculate, how to do calculations with impedance. I'll show many examples. Okay. That is, we are discussing electrical circuits, PYQs from BM paper, and this is actually part 4 of the 4-part series. This is going to be the last video series. Okay. So I want to see, again, the core idea behind the series is that approximately 80% of questions from roughly 20% of concepts in the whole syllabus. Our idea is to know this 20% of the concepts in and out. We have done most of those concepts. So what has left us? The couple of things. Okay. Phasor example, or I'll actually show you Phasor example. Very, very simple thing. Okay. I in part 3 have explained this elaborately, but basic Phasor example I will show you. So AC circuits with you can start doing the calculations that you already know. You know how to handle resistor circuits, right? You can treat it as resistor-like circuits. You can start applying voltage division, current division, typical things that you need to do. You can do series, parallel, all of those things. So you can treat it as a simple resistor-like circuits. AC circuits can have capacitors and inductors and resistors. But even given capacitor and inductors, you can treat it like resistor-like circuits. You can apply most of these principles if you use this thing called impedance. I'll show you a couple of examples of this. And you need to know complex arithmetic here. Okay, you need to know complex number multiplication division at a bare minimum. Okay, complex arithmetic. This is a must in order to do that. Again, actually, I have shared a playlist, biomedical signal processing or analog filters playlist, where I also explain this from scratch and show you simple examples on how to do this. If you already don't know this complex arithmetic, I have also explained that in a very short playlist. Okay, this is one thing. And then the worst case scenario, they are asking you for some frequency, you don't know how to answer that. The best guesses in that case is what I refer to as magic frequencies. I'll show you a couple of examples from PYQs. Okay, that's the objective for today. Let's get started. Okay, so this question I have kind of elaborately explained. I have also kind of reasonably explained the Phasor convention, but what they are asking for us, I'll put this in simple English so that you can fill the answer and we can quickly move on. Okay. Also, I noticed the answer key, official answer key is incorrect, right? So, but I think the correct answer is different. Okay. I'll in fact show let's find out the answer and then I'll explain that. Let's say we have the idea boils down to cosines and sinusoids or oscillating things, right? So you can actually look at circular motion and start describing cosines and sines. Okay, let's say a particle is traversing this in the counterclockwise direction. Okay, let's look at the x component and the y component. Okay, this x component, if this is a complex plane, notice this will be your real axis and this will be your imaginary axis in the complex plane. Okay, notice if the current location of a vector or a complex number is over here, okay, if this is at an angle theta, okay, you have the x component to be cos theta. If you make this unit circle, okay, for simplicity, the x component will be cos theta, okay, and the y component will be sin theta. What we mean by that is when the arrow is along here, it's the x component is a maximum. Then as the arrow traverses a circle, it kind of keeps on decreasing. The length of the x component decreases, becomes 0. So if you were to plot the component as a function of time, what you would be getting is, notice, essentially cos omega t. Initially, the x component is maximum. Okay, as it traverses, x component keeps on decreasing. Okay, notice as if here it decreases, as it goes here, it further decreases, right? It kind of becomes to 0 when the arrow is at this point. And then as it goes further, the x component becomes negative and reaches a maximum over here. And then the component reaches a maximum, becomes -1 and then becomes 0 again. And then as it gets back to the starting position, it completes a full cycle. And what we have here is essentially cos theta. Notice what we have here is cos omega t. The omega tells you how fast this arrow is rotating. So again, if you look at this component, if you look at the vertical component, you will be getting a sine curve. Okay, but to solve this question, what you need to know is the Phasor convention. What they are asking for us, what is the time delay between peaks of the voltage signal V1 and V2? So we have 2 cos 60 plus 60 degrees. and then V2 is minus 3 sine 60 degrees. I'm going to use phasor convention, and what we have here is essentially x-axis or the real direction cos theta, and negative y-axis. Okay, it's not y-axis, it's negative y-axis. Okay, that is sine theta. So in this convention, this direction is chosen to be cos theta. So with respect to the note that typically angles are measured this way, your positive angle is measured counterclockwise. Okay, that arrow direction is important, how you measure that angle. And if you measure it counterclockwise, okay, notice if you take sine theta, if you add 90 degrees to it, you get cos theta. And of course, if you take sine theta, if you add 180 degrees to it, it's the other way around. You are in the negative sine theta. You can start getting simple trigonometric identities in the simple phasor convention. Actual phasor convention actually boils down to representing this cos omega t as just a complex number. But let's just look at where is cos theta, where is sine theta for now. So the given two vectors, one is 2 cos 60 plus 60 degree. Omega doesn't matter in phasor convention. All you're looking at is where the arrow is with respect to the other arrows. Okay, so 2 cos 60 is over here. That is vector 1. Notice this is cos theta along x-axis plus 60 degrees, right? This angle is 60 degrees. That's the first vector. You have v1 of, okay, and then the second vector happens to be v2 of t is minus 3 sine 60. That is this vector. This is v2 of t, where I have drawn it opposite to sine theta direction, minus sine theta direction, 180 degree opposite. And the answer that we are asking for is, this is the time taken for this vector to traverse this angle is the time delay between the two peaks. Okay, what is the time delay between the peaks of the voltage signal? The peak of this happens here, the peak of this happens here. So the time taken for this rose vector to traverse this angle is the time delay. Okay, in simple words, what is the time period here? Notice omega happens to be 6. I am getting this from here, right? Notice we are only comparing signals with the same omega. We cannot compare signals with different omega on a phasor. This is notice this is omega is 6 rads per second. Okay, the time period will be 2 pi by omega. That corresponds to how many seconds? So notice, so I am moving from omega to time period calculation, right? Okay, some of you are saying the final answer, but okay, fine. This right now happens to be 2 pi by 6. So by definition, to traverse 360 degrees, it takes 2 pi by 6 seconds. So to traverse this angle, notice this angle is essentially total is this 90 degree and this is 60 degrees. So this angle is 60 degree. To traverse 30 degrees, it takes a fraction of the time period. Okay, it's going to be a fraction of the time period. So time period, a small fraction of it. What fraction? It's going to be 30 by 360 seconds. And this happens to be, time period is 2 pi by 6, that is pi by 3. And this fraction is, take that pi by 3, multiply that by 30 by 360. I suppose this is 10 pi by 360. And that is our answer. Okay. And notice the gate key is this, that is incorrect. I have plotted all the signals and I have showed it. Okay. This is gate key, official gate key, but that is incorrect. So this is, notice at the end of the day, so this is the phasor convention. Instead of looking at signals as a function of time, you are looking at how things are moving in a, doing the circular motion. And you are essentially comparing one arrow, relative motion of one arrow with respect to other arrows. Okay. Okay. Now, so AC circuits, if you know this impedance, we can do this resistor-like circuits, right? And then I also said magic frequency. Let's look at the next PYQ. The energy stored in the inductor is 6 joules. So we have a simple AC source inductor circuit. Energy stored is this much. The value of maximum power delivered in the inductors. See, the energy stored in the inductor at which instance is not clearly mentioned, okay? That makes it very ambiguous. And this is somewhat poorly framed. So I'm going to skip this. Let's not add fuel to the confusion. Let's skip this and move on to this question. Okay, what we seem to have is a RLC circuit. right? Let's zoom this. You can also zoom this slightly further. In the circuit shown below, it is observed that the amplitude of the voltage across a resistor is the same as the amplitude of the source voltage. The amplitude across the resistor is the same as the amplitude across the source voltage. What is the angular frequency? Omega naught in radians. Notice it's actually a second order circuit. You have a resistor, you have an inductor, you have a capacitor. But this is fairly easy to answer. Okay. Imagine if there were 3 resistors here. Finding the voltage across the resistor is fairly easy. You could apply voltage division. What seems to be complicating this is the presence of this inductor and capacitor, which is where the statement I made on impedance matters. Any AC circuit essentially becomes like a resistor-like circuit if you use impedance. I'll show this, and I also mentioned 3 magic frequencies, right? I think here let's see if the magic frequency works here, okay? Let me write down a couple of things. A bare minimal thing that you need to know you have a resistor. Let's look at the element here. You have a resistor and you have a capacitor, you have an inductor, and we have this ratio of voltage over I. Some of them perhaps technically can be a function of frequency. Sometimes that function is a constant, as in the case of resistor. So notice here we have, let's call this ZR, let's call this ZC, let's call this ZL, okay? This we know as the resistance R, okay? This we know as 1 by J omega L, which is fairly important. So I'm going to write this as 1 by J omega C, and this is J omega L, okay? And if omega is in radians per second, you're technically fine. Notice, without complicating this a lot, omega is in rads per second. That is one thing, the bare minimal thing that you need to know. Second, as I mentioned, 3 magic frequencies. Right? Let's do again, there is an RC circuit, there is an LR circuit. I refer to that as L over R circuit. And then sometimes there are RLC circuit, series parallel. Okay. And the magic frequencies, let's write this in frequency in hertz. Okay. So frequency in hertz, this is, you have 1 by 2 pi time constant RC. Here you have 1 by 2 pi time constant, that is L by R. This R goes to the numerator. And here you have 1 by 2 pi square root of LC. And just in case, there are a few other things. If frequency in case of in rad per second, often mistakes are done with this confusion between hertz and radians per second. Even traps are set there, so let me be explicit here. Okay, this is 1 by RC. Okay, this is R by L. This is 1 by square root of TLC. Just to remind you, notice this omega happens to be 1 over tau, where tau is a time constant in seconds. Again, notice for an RC circuit, this is RC. L over R circuit, this is L over R. And time constant, there are many time constants here. No, let's not finish this. So the first thing is, I'll show you how to solve that using impedance. I'll also show you how to solve that using magic frequency, or rather, let's use a magic frequency and guess if it works. Let's see if that actually we're also getting the right answer. So this is a RLC circuit. They are asking for angular frequency when the voltage across the resistor is same as the voltage across the source. At which frequency that happens, we actually technically don't know. Let's pretend, okay? Let's say method 1. Last 15 minutes of the exam, you're trying to grab a couple of more marks. And let's pretend you don't know how to solve this, okay? Let's see if we can magically guess the correct frequency. Magically guess correct frequency. And you want the frequency in radians per second. This is an RLC circuit, okay? So you have an RLC circuit. Okay. Let us guess. Is omega naught? Okay, we are only guessing. Okay, but let's find that number. In radians per second, this is 1 by square root of LC. If you stick to SI units, you are safe. Okay, Henry is in SI, Farad is in SI, Ohm is in SI. Just make sure you retain all the milli, micro, kilo and things like that. So the actual calculation that you have to do here is 1 by square root of 10 millihenry. So that is 10 into 10 power minus 3 into capacitance. That is 1 microfarad. That is 1 into 10 power minus 6. This is in SI. This is in SI. Your answer should be in SI. That is in radians per second. Can you calculate this and tell me what this is? And we don't know, we are just guessing. We are pretending we don't know how to solve and we are guessing, okay? We'll solve this and see if it actually works out. We'll do that in the method too. But can we find out what this number is? I suppose we have a square root of 1 by 10 power minus 8. So 1 by 10 power minus 4. I suppose we are getting 10 power 10,000. Okay. So right now I'm just guessing that. Okay. That's not the final answer. And the point of this being, just in case you don't know it. Okay. There are many places where the magic frequency is useful. Not just for this. Let me again point that one out. RC circuits, LR circuit, RLC circuits. This shows up in many other places. In bioinstrumentation. Sometimes models for PZT. Good model for PZT is a RC circuit. Good model for a cell membrane is a RC circuit. Okay. And then you have low pass filters, high pass filters in signal processing, right? Even circuits involving op-amps, analog circuits, active filters, okay? There are many other places where this resistor and capacitor element shows up, perhaps along with some other element, okay? Like an op-amp. It turns out many a times this magic frequency, this lower corner frequency, upper corner frequency, right? Actually does work in many of those problems, not just in RC electrical circuits and LR electrical circuits. So they are asking for your frequency. The best guess would be this, just in case you don't know. If you know, you can solve it, okay? I'm not stopping you, but just in case you don't know, try this, okay? So this is an example. So for example, the given PYQ is an RLC circuit. We guessed this, okay? Answer was in radians per second. So we did 1 by square root of LC. And let's now actually solve this, which is where I'm going to highlight this. And in fact, notice this is part 4 of 4, right? In part 3 of 3, I also made a statement, stick to SI. You are safe. Right? Stick to SI to be safe. I'm also doing some explicit calculations on that. Okay, let's do this. If you use impedance, how does this becomes like a resistor? Recall, okay, we have impedance of capacitor 1 by j omega c. This is j omega L, right? Let's go. Now, what we have here is ZR, ZL, ZC. Okay, voltage across a resistor. It's a fraction of the total voltage drop here. That is the 100. Voltage division. Let's see if we can apply voltage division with this resistor-like circuits. Okay, so I'm going to use voltage division, and what I say is voltage across a resistor is a fraction of voltage across, the input voltage is a fraction of the input voltage, and this fraction happens to be ZR by the total impedance, ZR plus ZL plus ZC. The three, this is almost like resistors, they are in series. The three impedances add up. One is ZL, this is ZC. Okay, but the difference is this is a complex number, this is a complex number, this is a complex number. Let's also explicitly write that. Okay, now notice your VR by VI equals ZR is R, ZR is R, and ZL is J omega L, ZC is 1 by J omega C. What we are saying is the amplitude, notice these are all complex numbers. They have an amplitude and a phase. Okay, there is a real part and there is an imaginary part. So what is mentioned is the amplitude of this are the same. So these two voltages are the same amplitude. So what it essentially says is this equals 1. Okay, let's also color code it so that this equals the ratio of the amplitude is 1. This is the same as the amplitude. That's why I'm getting that. At this stage, okay, we need to know some basic complex algebra. Notice this happens to be, if you know multiply and divide by j in the numerator and denominator, you get minus j by omega c, because j square is minus 1. Okay, you get this. And some of you are also wondering some basic things, right? Some very basic complex numbers I will do. Okay, if z is this complex number a plus j b, okay, you can write this in a slightly different form. This is amplitude angle form. Okay, this if you take a look at a circle, take components, you can easily get it. Okay, let me also say that over here. Just notice your given complex number is over here. Now this is the complex plane. So this is the real part, this is the imaginary part, and the complex number that you have here is a plus jb. The real part is a, okay, real part is a, okay, the imaginary part is b, and the length happens to be r. How do you find the r? R happens to be square root of a square plus b square. This is your amplitude, and the phase is this theta. How do you find theta? That is also fairly simple. Theta happens to be tan inverse of b by a. So given a and b, you can find r, and given theta, given r and theta also, you can find this. So you can take components, this given r and theta, I will also write those relations. Notice given a and b, you can find r. Given a and b, find you can theta. The other way around, notice a is just r cos theta, b is r sin theta. So given r and theta, you can find a. That is something. Sometimes we also write it as in a different form. This is actually in Euler's form, polar form. This is e power j theta. Notice the Phasor convention, the shortcut for r into e power j theta is actually, the shortcut is this. Write the amplitude and write that angle or the phase over here. Angle next to it. Okay. So, and we have the one important element, the conjugate. This is often z bar or z star. This is essentially the a minus jb. Okay, the conjugate is here. The angle phase is negative. Okay, x component is the same. Y component, the imaginary part, is negative minus b. Okay, often the conjugate is useful. And so notice we got the amplitude here, we got the phase here, and then we also got the conjugate here. So this amplitude happens to be equal to amplitude of numerator by amplitude of denominator. Amplitude of numerator is this. Amplitude of denominator is a square plus b square. R square plus, notice this is j omega L minus j by omega c. So the amplitude of that will be omega L minus 1 by omega c whole square. Okay, what I have done is to use this relation. Notice I said 1 by j omega c is minus j by omega c. I made that substitution and then took the amplitude. It's square root of a square plus b square. Now the question is, what we have is a real number. We are only looking at amplitude. When is this equal to 1? Can you stare at this and tell me at what frequency this becomes? The numerator and denominator cancel each other. Yeah, one is to say that resonance frequency, another one is to say that, notice, if this term is 0, when this term goes to 0, numerator and denominator cancel each other. So that happens when your omega L equals 1 by omega c. And this implies the omega of interest, right? Omega naught square is 1 by LC. And this happens to be 1 by square root of LC. And stick to SI, you're going to get an answer in radians per second. If you calculate this, what should you get? Yeah, what you get is 10 power 4. See, notice there was a reason We guess magic frequency, right? That happens to be the resonant frequency here. That happens to be the frequency at which the impedance is minimum. Current flow is maximum. Total impedance is ZR plus ZL plus ZC. When is that a minimum, right? Again, that minimum happens when omega L equals 1 by omega C, right? So notice, hey, here we kind of smartly guessed. Try to smartly guess magic frequency. Does it magically work? In this case, it worked. Okay. Here we kind of solved it. Our guess happened to be correct. Will it always be the case? Not necessarily. Here it turns out to be correct. Okay, point number 1. And notice, for RLC circuit, let's just say circuits. Okay, this omega naught equals 1 by square root of LC. Okay, this is what I refer to this as the magic frequency. Magically gets you the answer. If you go search Wikipedia for magic frequency, will you find magic frequency? No, this is just a mnemonic. Okay, magic guess. Magic frequency in rads per second. That is also important. So this is a rad per second. This also happens to be the resonant frequency. What is the frequency at which there is resonance between input and the network? Okay, so also resonant frequency, but for both series parallel. This also happens to be the frequency at which impedance is minimum. Frequency at which net total Z is minimum. And that also implies this is also the frequency at which total current drawn from the source. Okay? Total current is maximum. Actually. And when I say minimum, this is amplitude, total amplitude of current. Okay, this is when the resistance is the least, current flow is the highest, right? So current is best. So it shows up in many places. And this is both series parallel, and there are many interesting details associated with it. We already see this, right? Notice amplitude of the impedance is this square root of R square plus omega L minus 1 by omega C, right? This will be a minimum when this term is 0. That is a square term, right? End of the day, it's going to add some value to this R square. If that is 0, that is when this whole thing is a minimum, right? So impedance is minimum, and the impedance amplitude that is minimum, you have the maximum current. So this magic frequency corresponds to so many interesting situations in the circuit. That is why, it is ubiquitously shows up. That is the reason, probably this is the frequency they are asking for. Having said that, if they are modifiers here, use common sense to retain the modifiers. For example, if this is a microfarad, when calculating, we retain the micro. Farad is in SI, we retain the micro, right? Henry is in SI, milli, we retain that milli, right? We did that calculation. If they are modifiers here, what is 1/10 of the angular frequency, right? So your magic frequency is 10 power 4. 1/10 of that is answer B, 10 power 3. So if there are modifiers in the question, retain the modifiers. Okay, find the magic frequency. Whatever additional trap is added there, it is what is twice the angular frequency, what is half of the angular frequency, what is angular frequency plus 2, something like that. Whatever modifier is there, typically set as a trap, retain that modifier. In this case, no modifiers, just the angular frequency, directly your guess. In case they are asking you 1/5 of the angular frequency or 1/10 of the angular frequency, notice if they are asking for 1/10 of the angular frequency, I would have calculated 10 power 4 and then did 1/10, that would be 10 power 3. So my guess would have been B. Okay, so retain modifiers. Now, so at this stage we have seen 2 things. In fact, we have seen 3 things. AC circuits kind of become like a simple resistor-like circuits if we use impedance. Only complication there is it involves complex arithmetic. We have seen use of magic frequency. Then, stick to SI to be on the safe side, right? We have also seen calculations. Let's go to this PYQ. For the circuit below, choose the angular frequency omega naught at which the voltage across a capacitor has maximum amplitude. Okay, let's also do the magic frequency. I think this is an example where the magic frequency guess doesn't work, but let's try it. Okay, method 1, magic guess. Our circuit is RC circuit. So the frequency that I am going to guess is 1 by RC. And if I have to calculate this, notice this, if you put, this is 1 into 10 power 3, and that is 100 into 10 power minus 6. Where answer should be in radians per second. Can we calculate this? What do we get here? I suppose this is 10 power 5 and this is 10 power minus 6. I suppose this is 10 rads per second, 0.1. 1 by 0.1, that is 10 rads per second. The answer notice is not there. So probably, this is an instance where the magic guesses doesn't work, okay? I'm not saying it works everywhere. It doesn't work in this case. So let's try to solve this. Method 2, where we solve. Okay. Voltage across a capacitor. How do you do that? If you use impedances, you can do voltage division. So what I'm going to do is voltage division with impedance. So notice the voltage across the capacitor is a fraction of the input voltage. This happens to be 100. And notice this is cos. So this is along the real axis, okay? Or it has a phase of 0. I'm not writing that. Okay. This is going to be ZC. It's a fraction of that 100. What fraction? ZC by total. ZR plus ZC. Okay. So at this stage, notice VC happens to be 1 by, or let's write it this way, 1 by j omega c by R plus 1 by j omega c into 100. And if you have to take the amplitude, notice the amplitude of, technically there is a 0 degree phase. If you take the amplitude, it is exactly 100. Okay, length of that is 100. Again, let me do this calculation once. You have 1 by j omega c, and what you have here is j omega cr or rc plus 1, okay, by j, the whole thing by j omega c. I just added the denominator, j omega c. If I take the j omega c to the numerator, this thing cancels. What you are left with is this into 100. So what we want is the frequency at which amplitude of the voltage across the capacitor is 1 by, amplitude of the numerator is 1, amplitude of the denominator is square root of the real part, 1 square, plus square of the imaginary part, omega square r square c square. And that into, of course, I have to retain that half. So at what frequency is this thing maximum? When is this term maximum? Now the question boils down to, when is this maximum? When is this max? Equivalently, that happens when is the denominator minimum? When is the denominator minimum? At what frequency is the denominator minimum? This says denominator will be a minimum when omega is 0. So this is denominator is minimum. That happens when omega is 0. So your answer by solving here is D0. And this is an example where, of course, the magic frequency that we calculated doesn't work. Fortunately, notice, okay, they didn't put the trap. If I were the examiner, I would have put 10. There are cases, many, roughly 8 out of 10 questions, magic frequency works. Many complicated analog filter circuits and all, it works. There are 1 or 2 examples where it doesn't also work. This is one such example. And notice, if we use impedances, I just applied voltage division, right? There are 2 impedances. There's a ZR and ZC. There is a ZR and ZC. And I simply solved. Hey, when is this maximum? You're not going to solve this. Take the first derivative, set it to 0 and all that. Okay? Again, that is a step that I might have taken for granted, but you need to get used to it. This comes with practice. Notice, hey, when is this term maximum? When the denominator is, this is a function of frequency. At what frequency is this maximum? Hey, this is 1 divided by denominator. The smaller the denominator, the bigger that resulting number is, right? The smaller the denominator, the smaller the number you divide 1 with, bigger the number you get. You have 1 cake. Now you have to split it between people. The smaller the number you divide it with, the more cake you get. There are 10 people, of course, you are going to get 1/10 of a cake. If there are only 2 people, you are going to get half the cake, right? If there is only you are going to get the whole of the cake, right? So the smaller the denominator, the smaller the thing that you are dividing with, the bigger is the resulting thing. So this whole term, this ratio is maximum when the denominator is minimum. Yeah. Again, so this tiffin box, lunchbox dabba, and then this cake. Kind of these examples or analogies are always more relatable, I suppose. So it's also easier to explain. But actually, that's a fair question, which is what I was also mentioning. I kind of took this for granted, right? I didn't do, this ratio is a function of frequency. I'm trying to find the frequency at which this function is a maximum. The typical way of doing it is, calculus way of doing it is take derivative, first derivative, set it to 0. Hopefully the second derivative test kind of is like fine and all that, right? But we are also kind of seeing like simple English, right? And this will save you a lot of time. And we also need to be careful while doing it. And typically that comes with practice, okay? This is one example where I did it. I also actually did it the previous question. When is this thing 1? In fact, even in this question, notice, 1 is to say when is this ratio 1. There we can, hey, if this term, two things get cancelled, right? We get a 1. That is to say one thing. Equivalently, they could have asked, when is the current in the circuit maximum? Current in the circuit is maximum when the total impedance is minimum. The total impedance is this denominator. That happens when this thing, you are adding a square term to r square. You are adding a positive term to r square, right? If the square or your term you are adding a 0, that is the minimum that you can get, right? So when we did the same step here, right, we kind of took it for granted, but equivalently they could have stated this as when is the impedance, total impedance of this is a minimum. Notice I already put that over here, right? Frequency at which total impedance is minimum, or equivalently frequency at which total current in the circuit is maximum. Current drawn from the source. Okay, great question and a fair question, okay? And that's the answer. Let's move on. Say from now on, it's mostly Kirchhoff's law, I suppose. Yeah, I solved this problem recently. It looks like a lengthy problem, but I'll do this, okay? Series RLC circuit is connected for a fixed value of R and C. Inductor is varied to deliver maximum current. This value is 0.4 amps. So notice, you are fixing, it's an RLC circuit, you are fixing R and C. You are varying L. If you vary L, you are changing the resonant frequency of the circuit. As you change L, it's a different circuit. It has a different resonant frequency. You keep on varying it until this circuit's resonant frequency hits this input frequency, 50 Hz. That is when you get the maximum current, okay? And that maximum current happens to be 0.4. So at minimum impedance, you have maximum current 0.4. And the potential drop across the capacitor, I suppose they are referring to the amplitude. The amplitude of the potential drop is 330 volt. The value of the inductor is, okay, this is, if you are kinda not careful, this can take a lot of time, okay? So anyways, let me do this. You have a inductor, capacitor, or I am varying this, let's just, you could draw this in whichever order you want, it doesn't matter. Series RLC, right? You have a series, so I draw a series circuit. You have R, okay, and you have ZC as 1 by j omega c, and then there is a variable inductor. This is variable. You keep on changing this, so as you change L, you change the resonant frequency and of the circuit. So this Z L is j omega L, and this is at 220 at 50 Hertz. So the first point that I'm going to focus on is maximum current, max current. Let's say the current I, okay, max current. This implies minimum impedance. That is R plus j omega L minus j by omega c. The magnitude of this is minimum. When does this happen? Your omega square is 1 by LC. Okay, so you are keeping on varying the inductance so that the circuit's resonant frequency becomes this input frequency 50. Right? Right now, omega, you don't know the capacitance. You know the capacitance, you can find that. For that, I suppose one more thing is given, right? And notice in this scenario, when omega L equals is minimum. Let me also write it, slightly more elaborately, okay? Notice that is R plus J omega L minus 1 by omega C. This is a minimum, okay? That is when omega L equals 1 by omega C. This is what we refer to as the reactance. The imaginary part here is referred to as reactance. They cancel each other. Or when omega square or omega happens to be, omega square is LC, omega happens to be 1 by square root of LC. Okay? So essentially these two are cancelling, right? That tells us the max current I max happens to be input V, okay, divided by Z min. Z minimum is just R when these two cancel each other. Okay, this is Z min. I'm going to write that as Z min. Okay, and Z min is just notice if that cancels, it's just R. So you have 220 by R. That is R is given, but R is not, max current is given. So this is R. Right. Notice this happens to be 0.4. So you can find R from here and you'll get that in ohms. Can we quickly get the R value here somehow? And then we have to find the capacitance value and then we have to find the inductance value. Again, the same thing, right? The impedance here is going to be, Dinesh, we have current is maximum and impedance is minimum. Impedance is amplitude of the impedance is this amplitude of this complex number, complex function, okay? So it's going to be square root of R square plus this imaginary term. Imaginary term is that frequency dependent term, and the frequency dependent term is 0. You have the, see, if Z is A plus JB, magnitude of this is A square plus B square, square root of that, right? Typically this imaginary part happens to be function of omega, right? And so often Z minimum, it's a sum of two positive terms, this square plus this square. You get this minimum when if B square omega can be 0, that is when you have the minimum, right? This happens to be A when that this function is 0. B omega is 0. B square omega or B omega is 0. Or that imaginary part or B omega is 0. That is the imaginary part is 0. Okay. So this is the same thing that I have been doing for a long time now, actually. It again boils down to the magic frequency. Hey, when is this amplitude maximum? That happens to be when this denominator is minimum. That is when that imaginary part is 0. Notice I already said that, right? Actually that corresponds to Z minimum, I maximum. And if I have to isolate that detail, it is here. Typically this, this only this capacitance and impedance, inductance, that has this function of frequency. For the resistor, it's not a function of frequency. So the real part resistance is typically, there is no omega term here. So omega at which you get Z minimum, this is when, the omega when this imaginary part is there. Is it clear, Dinesh? Fair question. But it's the same thing that I have been in 2-3 problems, the same thing that we have been looking at. Yeah, when is this current maximum minimum impedance that happens when this imaginary term is 0? Okay, yeah, this is where we have great. Fair question. In fact, I am happy that some of you are stopping me and asking these questions because it's better to clarify. At the end of the day, it's a simple question, but and then now we have to find the capacitance and then only we can find the inductance, right? We also don't know the C. For that, one more piece of information is given. The potential drop across the capacitor is 330 volts. So VC is fraction of the voltage across the capacitor is essentially ZC by total C. ZR plus ZC plus ZL. I'm applying voltage division. All this is of the input. Okay. And technically we are looking at I presume, they are talking about the amplitudes. Okay, this is presumably amplitude. It's not explicitly stated, but that's a fair presumption. Okay, presumably amplitude. Okay, so what we have here is this is 330 happens to be 1 by J omega C by R. Hey, we are already talking about this. At 50 we know this is cancelling, so that is 0. Okay, we know this is getting cancelled, the same frequency, or we have changed the inductance so that that frequency is where this cancels, right? So we don't have to worry about this term either. The amplitude of this into 220. This is also actually notice fairly simple. This is just 1 by omega CR. Amplitude of J is just 1. So this is 220. I suppose we know omega, we know R. Can we find C? We find C, then we can go plug in and find L here. Okay, here there is a trap. So let's just find C, and then I'll tell you where the trap is. C is 220 by 330 into 1 by omega R. And you should technically get this in farads. So I'm asking you to do the calculation because there is a trap. See, at this stage, I am also recognizing something. Okay, I need to make a comment on that. Great. The current answer is supposed to be 3.86 microfarad. Okay, 10 power minus 6 farad. You won't get this if you put omega is 50. Okay, F is 50 hertz. Omega is 2 pi into 50, that is 100 pi rad per second. Is a typical mistake that happens. Yeah, just plug in all these numbers, you'll get this, okay? But if you plug in 50, you won't get that, okay? This is 220 by 330. Yeah, there is only a calculation, there is nothing to explain. This is 2 pi f, that is 100 pi into 550. That should give you, or you're referring to this step, I put this J0. Again, so no, there is a nice connecting word here. See, I said there is a poorly framed question, right? Notice, the current is maximum. That maximum value is 0.4. And corresponding to that, the potential drop across a capacitor. So the potential drop when that ZC and ZL cancel each other, that is when the current is maximum, right? That is when this term is not really there, right? It is 330. So 330 is, this into 220. And notice this fraction, some of you might be wondering, so how come, we have input is 220, this fraction is 330, something only across capacitor it's 330, higher than what we apply, because, we also need to account for phases and there is an inductive element, okay? The capacitive phase and inductive phase kind of cancel each other and all that. Because of that, voltage across the capacitor or the inductor can be higher than the input voltage. What is happening is parts of that are getting cancelled. At least the phases are getting cancelled. Okay. So I am essentially reusing the same thing. Maximum current happens when the imaginary part is 0. I'm just reusing that part. I don't have to worry about that. So the amplitude is just R. And if you want to be slightly more clear here, all I am doing is, this is amplitude of 1 by j omega c. Okay, yeah, amplitude of 1 by j omega c is 1 by omega c. 1 by omega c. And then amplitude of R is R. So this happens to be 1 by omega RC into 2. Okay, there is a 220 there. Okay, 1 by omega RC into. And again, I have underlined the detail that I have kind of used it. Maximum current, the corresponding potential drop. The corresponding is a connecting word. That is the important word. Okay. So it boils down to, the maximum happens at the same condition when this net impedance is essentially purely resistive. And this is a typical mistake that students do. Be careful about this. So this is 3.86 and I think we can find what this is, right? Now your L is finally, hey, at this stage, notice for me, I am quite generous on how I am using the space, right? But typically when I cross 2 pages, that's typically it's a that's a quick rule of thumb for me to actually in the real exam. That's a rule of thumb to suggest I am possibly wasting time in one question. Okay, the most important time management tip is limit the amount of time you spend on any one question. Most important time. The exam time management tip. This is the most important, okay? Most important exam time management tip, okay? That is, limit the amount of time you spent in any one question. Limit total time spent in, max time spent in any one question. Max time spent in any question. And this is approximately, let's say 9 minutes. So should I keep on checking the watch? No. Okay. Your rough work, you're given a a rough note to actually do all those calculations, derivations and all that. Your rough work, it's approximately, and let me write it, okay, approximately more than 1 page. Certainly more than 2 page, you are wasting time. You are spoiling, because of one question, you are spoiling your entire examination performance. So by the time your rough sheet is full, that's a sign that you're possibly wasting time. However favorite topic it is, how much ever preparation you have put into that one topic, how much ever confidence you have on solving that question, how much ever interest you have on that concept, whatever, irrespective of all that, that 1 or 2 marks is not worth it. Okay, you can keep your interest, curiosity, determination, all of that aside for that one question that takes more than 1 page. Okay, this specifically applies at the beginning of the examination. You have some excuse at the last 15 minutes, half an hour, when you think you are done with most of the questions, but limit the maximum amount of time spent in any one question. No question is worth your time, worth more than 10 minutes. Your confidence gets affected. Hey, what I am like, I'm not able to solve this, I'm somewhat getting stuck. You're losing your momentum. Okay, and the time you waste, you say you didn't keep track of your clock, or you didn't keep track of your rough work. All of a sudden 30 minutes is gone, 45 minutes is gone in one simple magic frequency question. That's it, right? Consider the impact of that. You don't want that happening. Okay, so any question you shouldn't be spending more than approximately 9 minutes. Okay, be very careful about it. In fact, in the lecture I kinda hit that border when I cross 2 pages. Your exam rough sheet, your font size is different. Okay, you will have to kind of fine tune it, but based on my font size, the lecture space that I use, roughly when I'm hitting like 2 pages, I know, hey, this is taking a long time. But because I'm not solving the examination, I'm explaining this, I went ahead. Okay, so finally your L happens to be 1 by omega square C. Again, if you stick to SI, you should get the answer properly. This should be in Henry. What is that? Can someone do me the favor of calculating this? Omega, you just found out C, 2.6. I suppose, yeah, that's there in the answer key range. 2 point. Yesterday I solved this, I got 2.63. Okay, again, stick to SI, beware. 1S, beware. Another thing, stick to SI, you are safe. Stick to SI units to be safe. Approximately 2.63. Okay, around that number, based on your approximation for pi. Sometimes there is a change. Also notice you are not doing the calculation on one go. You're not doing, you're finding resistance, you're finding capacitance, and then you're finding inductance, right? Some of the this errors in the decimals can propagate, and they give some room in the answer key to actually accommodate that, so you don't have to worry about it. But fair questions, and in fact very great participation, and fortunately slightly, but by this time I kind of knew. I almost got the answer. Okay, and also I am explaining this, so I went ahead and solved it fully. In the real exam, at this stage I would have wondered, and often I would have actually went to the next question. Hey, I put 10 minutes in that question already, right? Waste of time. Fine, let the 10 minutes go to waste. Let me save it elsewhere. Okay, fine. 8. A series RLC circuit with, hey, so some of you said second order circuits is problematic, right? But notice the number of second order circuits that we have been solving. This is a second order circuit. Okay, this is a first order circuit. This is a second order circuit. The idea is, if you use impedance, there is no distinction between first order and second order. AC circuits kind of become like resistor like circuit. You are not worried about making like 4 resistors. You are not bothered about it, right? 3 resistors. Same thing happens with second order circuit. If you know that complex algebra, you can easily deal with second order circuits. Okay, so by now you should have actually gained confidence regarding that. Okay, there are, I think, two more PYQ. Okay, I think given time constraints, I will solve one. Okay, I'll solve this PYQ, and I'll also explain some basic theory pertaining to this. Notice again, this is an RLC circuit. Consumes power P. Value of L is same as that. This circuit consumes same power P, but operates with a lagging power factor. We have a new term, lagging leading. right? I haven't explained that. That needs some theory. So I'll explain minimal theory. I'll solve this problem. And this power factor question is also a very, very important topic. Notice there is one more question. I think in 2021 showed up. Okay. This question, actually, it's actually a very easy question. Easy if you understand terminology. And I have put up a video, 5-minute video kind of explaining this terminology and with a solution to this 5-10 minute video. Okay. What I will do is, in fact, if I make this video public, I will add that video here in this video so that you don't have to go search for that. This is if you understand terminology. Okay. It boils down to actually finding, calculations with sides of a triangle. Calculations, adding and subtracting sides of a right triangle. Calculations involving sides of right triangles. Okay. This is actually fairly easy. Okay. Just calculations of, involving sides of a right triangle. I'll share that video. Okay. I'll in fact add solution discussion here. Okay. But this question is answerable with impedance. Okay. Whatever impedance that we have been talking about. So regarding that, we have this mnemonic. Let me start with this mnemonic. Okay. What is leading, lagging, and all that? Leading and lagging show up in the context of, notice, voltage and current are not in phase. Both are complex numbers. If you look at, say, voltage, phasor, the current phasor is not along that whenever there is frequency dependence. This is elsewhere. So there is a phase difference between current and voltage. Okay. And then is the current ahead of the voltage or behind the voltage is where this phase leading and lagging show. If the current leads the voltage, okay, you have a leading power factor or leading power consumption and all that. In this case, if now let's say the voltage somewhere over here in the circle, at that point the current is lagging, right? This is often referred to, current is lagging behind voltage. With respect to voltage, is the current leading or lagging? That is the question. So with respect to V, notice this is phasor, is I leading or lagging. In purely capacitive circuits, this angle is often 90 degrees. Purely inductive circuits, this angle is often 90 degrees. But in a combination with a capacitive RLC circuit, this angle need not be 90 degrees. Okay. And so is it capacitive or is it inductive? Is a leading circuit capacitive or inductive? The question, right, often shows up. And we have very simple mnemonic for that. We have C, I, V, I, L. In a capacitor, current shows up before voltage. Okay. So current I is leading voltage. Current is leading voltage. In an inductor, L for inductor. Sir, I for inductor. What is this? L for inductor. Inductance, right? Your current is actually lagging behind voltage. So civil is the mnemonic that we use. And what is shown here is almost, it's the same power. The impedances are the same. Magnitudes are the same. But there is a change in the dominance. Is it more? Notice if it is lagging, say if it is like capacitor is dominating, now the inductor is dominating. Okay. Again, what do we mean by that? Let's just give more example. Let's calculate. Notice right now we know all the traps. Your F is 50 Hertz. So your omega is 100 pi rad per second. Quickly, can we have ZR is 10? Okay. ZC, this is 1 by j omega c. Can we have a calculation here? Okay. At the end of it, they should have units of resistance, okay, magnitude of that, and then ZL, j omega L. Can we calculate the number? Magnitudes will be in ohms, okay. I suppose this is going to be minus j into some number. This is going to be j into some number. Capacitance is given 100 microfarad. So omega into omega c. So how much is this? I have 100 into 3.14. That is pi into 100 into 10 power minus 6. 1 divided that. I have 31.85. ZL is 100 into 3.14 into L is 50 milli. 15.7. So what they are saying is Z init, initially this is 10, okay, minus J into 31.85 plus J into 15.7. This is, notice, 10 minus 31.85, right? This is J into 16.15. This is your Z initial. And notice this is actually minus J. This is capacitor is dominating. This is actually leading. C is dominating. There are both capacitor and inductance, but C is dominating. That is why you have a minus J on a net. Now this is being, the value of L is changed such that consumes the same power. Let's also highlight, consume the same power. Okay, that what that says is magnitude of Z init equals magnitude of Z change, Z new. Impedances are the same, so power consumption is the same. Okay, but operates with a lagging power factor. So your Z new is lagging, your inductor is dominating, same power consumption, so magnitude is the same. So this is essentially plus J into 16.15. Notice this is lagging and now L is dominating. So you have to increase the inductance so that this becomes L is starting to dominate. How much should you increase? The new value of L is, that is what they are asking. The new value of L should be much higher than the old value. Okay, L is dominating. What is the L new that will give this? Okay, and that boils down to, notice, J omega L new minus, you don't change the capacitor, that happens to be J into 31.85. This should be equal to J into 16.1, right? So Z new is giving this is giving this term. Okay, here we are changing Z. Here L is changed. In fact, we can actually see that L needs to be increased. What is L? The J's and all that will get cancelled. Perhaps if you're kind of wondering, all I'm writing is Z init is Z new. Okay, the Z new is this. So you can also have technically R on both sides. Sir, where is that R went, right? You can also have that R that is also getting cancelled. So I'm not bothered about that. So the new change, right? If you put this, your capacitor remains the same. The net is plus 16.15. You can find L new. What is the value of L new? Be careful. My L new happens to be solving. So it is 16.15 plus 31.85 divided by omega. Let me be explicit. This is 16.15 plus 31.85 divided by omega, that is 100 pi. I suppose this is 0.15. Let's do that calculation. Okay, 0.15 plus 31.85 divided by 100 divided by 2.14, 1.053, and they want the answer in millihenry. So that is 153 into 10 power minus 3 Henry. Notice this is in Henry, SI, right? That essentially is millihenry. In fact, if you want to retain a couple of decimals, I got 158, right? So like this is 152.8, 8 or 9. Okay, yeah. Be careful. The answer is in millihenry. Simple traps. That's it. A very simple question. So consumes the same power, says the impedances are the same, but initially it is leading, capacitor is dominating. You are increasing the impedance. Notice 50 became 152. You have increased the impedance so that it became a inductor dominating circuit, or it became a lagging power factor circuit. Inductor dominating is referred to as lagging power. Okay, so this is close to our scheduled time. As I already said, okay, this question actually calculations involving sides of right triangle. Notice this power factor question keeps showing again and again. Okay, so I'll add the already discussed solution to this video before uploading it. Two loads are connected to AC supply mains as depicted in the figure. One load draws 10 kilowatts, whereas the other load of 10 kilovolt ampere is operated at 0.6 power factor lagging. To achieve an overall power factor of 0.9544 lagging, the nearest kVAR rating of the capacitor band
needed to be connected across the supply mains is equal to. Okay, so essentially we have a AC supply. There are two loads. Okay, let me explain what this is in a moment, but we want to add another capacitor to this so that we end up with the overall power factor of this being 0.9544. These circuits, the voltage is not in phase with the current, right? So just the product of voltage and current, that's known as the apparent power. Okay, but if you look at the component that's where the voltage and current are in phase, VA cos phi, right? That's called the active or real or true power. Okay, and the component that's not in phase, where the voltage and current is not in phase, that's called the reactive power. Units for this is volt ampere, watts, and volt ampere reactive. Okay, and the power factor here is essentially the ratio of true power by apparent power. That's a power factor. Okay, so for given any loads, it's a good idea to just draw the power triangle. The nice thing is you can add and subtract sides because they satisfy complex arithmetic. Okay, for example, so let me explain what you mean by that. So 10 kilowatts. So the power triangle corresponding to this load 1, is just a single line because all of it is active power. There is no reactive component. Okay, that's also equal to the apparent power. So this is a triangle with 0 height. This thing. So 10 kilovolt ampere is the apparent power. Okay, power factor lagging. Lagging means this triangle is facing upward. Leading means triangle is facing downward. So power factor is 0.6. So ratio of this by this is 0.6. So this is 6. Okay. So this is 6. This is 6. This is a right triangle. So this should be 8. Okay. Now they satisfy, you can add and subtract size, base and height. So if you add these two, the net triangle for this is 10 plus 6, which is 16. That's the base of this. The height of this is 8. So this is where we are currently, the black triangle. We want to end up at a red triangle whose power factor is 0.95. Okay. So 16 divided by 0.95. Okay. That should be the length of this. That's the definition of power factor. So that turns out to be 16.76. Corresponding to that, the height over here is 5 kVAR. Okay. If 8 has to become 5, we need to add a capacitor that has a leading downward triangle. This is a triangle with just no base, just the height. Okay. We need to add a triangle of, we need to bring it down by 3 kVAR. So this is the effect of the capacitor. There is no active true power in a capacitor. Just all of it is reactive power. The value we want is 3 because that will bring 8 down to 5. So the answer here is option E, which is 3.
And that brings us to the end of it. Okay, what is there is, there are a couple of more miscellaneous things. There are like simple BJT MOSFET models, right? For this is, for example, current gain in the circuit below. There is a dependent current source. But this can be simply again analyzed using the same tools that we already know. Okay. So the current here is going to depend on the current here. And finding the current here, notice current division, you can find the current here. So this is 100 times that current. Once you know this is 100 times that current, notice these two are not separated. That is, what happens in this circuit doesn't affect what happens in this circuit, right? There is no net flow of, this is not a closed circuit. So find the current here and then again current division, you can solve this. Okay. Fairly, 2 current divisions, you get the answer. But this involves this new concept called, there is a dependent source, but fairly easy. Okay. If you look at 2022 discussion, you can find the solution for that, and then that's it. So at this stage, these are questions from measurement, I suppose. It looks a circuit is given, but hey, which is accurate, which is precise is a measurement question. So, but it's a good place to, stop. Our objective certainly is met by now. 80% of questions show up from 20% of concepts. You need to know the 20% of concepts in and out, all the things that discussed in this 4-part video. If possible, I'll make it one video. All the 4 parts I will combine into one video. I'll put it hopefully before the GATE 2025 exam. Okay. If you know that in and out, electrical circuits, about 10 marks is showing up every year. You can you can score a lot in that part. Okay, conclusions. So today we looked at AC circuits. Hey, this is the same old resistor circuit using impedance. Catch, you need to know complex arithmetic. First case, we are asking you for some frequency. You don't understand the question, otherwise, other than the word frequency, you don't understand. Try guessing magic frequency, worst case scenario. And certainly if it's a NAT question, right? No negative marks. Stick to SI, okay? You don't have to worry about units. And the most important takeaway, not just for circuit, for every other subject, entire GATE exam, the most important tip is beware of the time you spend on any one question. Shouldn't exceed 10 minutes, okay? Your amount of rough work you do is an indicator of that. You don't have to necessarily keep staring at your watch. Wasting time staring at your watch, right? Panicking staring at your watch. Fine, beware of the time you spend on any one question, okay? So that's the last thing that I have to say. And this, we conclude this 4-part series, okay? I hope this will be useful not just for biomedical students. If you are, electrical circuits is there in many other papers, right? Instrumentation paper, electrical engineering, electronics and communications, EC paper, EE paper, IN paper, BM paper, all the students, right? Many of the students are trying to clear the cutoff. I am sure this 4-part videos series should be of immense help to all those students. Even otherwise, I know this is a good starting place to actually get started with circuits. There are more advanced things, right? There is 80% of concepts left, but most of the scoring can be done here. And with the way we discussed, and if you know all those things in and out, you can do very well in electrical circuits, okay? You can easily score more than 80% of the questions from electrical circuits. And our objective is met. With that, with no other questions impending, I think this is a good place to stop.